Good day, everyone, and welcome to the 19th edition of the group exhibit Hydrogen and Fuel Cell here at the HANNOVER MESSE 2013. I invite the public to come and join us to discuss some interesting subject regarding hydrogen electrolyzers. We offer drinks and soft drinks, so have a seat and join us. We'll be discussing today, I'll have the pleasure to discuss building meaningful scale hydrogen electrolyzer 10 megawatt and beyond. Please help me welcome the board member at Ceram Hyd, Dr. Tarek Massar.
Thank you.
Thank you for joining us.
Thank you very much. It's my pleasure.
So as per the subject today, building meaningful scale, without, no pun intended, but why do size matter?
Why does size matter? Well, this is essentially, I would say, client-driven. Until now, we are seeing the biggest actual drive today in the hydrogen industry, specifically in the hydrogen production industry, coming from utilities and coming from industrial gas suppliers. For utilities, for instance, power to gas, which we could probably talk about a bit later on, the actual scale that they would be interested in is well beyond even the megawatt scale. I mean, talking to them about 100 kilowatt does not actually in any way move the needle for it. They're interested in 1, 5 megawatts, 10, 20 megawatts eventually for the actual scales that they are operating at. The same actually applies also for industrial gas suppliers, because industrial gas suppliers currently supply hydrogen mainly out of steam methane reforming, natural gas. And these systems are very big. They're made to produce literally thousands upon thousands of kilograms a day. And existing electrolyzers are not. So anytime basically industrial gas suppliers need to make an actual installation of a system for the production of hydrogen from electrolysis, they are essentially an order of magnitude off. And the exact same applies in the case of utilities. So this is essentially, I would say, driven by client demand. This is where this is the actual scale which is meaningful to the client.
So you're saying this demand to go bigger is driven by the end customer, if you want.
Absolutely.
Where have we seen similar growth necessary first, to bring the scale out before you see it taken by the end customer? Is there another market where we could parallel this process?
Yes. Actually, there's a very even striking amount of similarities between it. In the water market, for instance, we're talking about almost 15 years ago, when they first introduced membranes, such as the reverse osmosis membranes, the ultrafiltration, nanofiltration, all of these membrane things for water purification and treatment, initially they were essentially lab-sized or meant to essentially purify cubic meters an hour, a couple of cubic meters an hour. The scale that was required was more like thousands of cubic meters an hour. So originally, all water plant operators saw that actually there is obviously an advantage in using the membranes. They give the required characteristics. They are more durable. They produce better water quality, etc., etc. But it just was not at the kind of scale they wanted.
So the technology had advantage, like you say, in terms of filtration, but it was not adopted by the end customer because the scale wasn't matched.
Right scale, exactly. And it was an order of magnitude off easily.
And you believe that in fuel cell industry is the same, we're in the same parallel?
I think in the fuel cell and the electrolyzer, the hydrogen production industry, it's exactly the same parallel right now. When we talk about electrolyzers, when we talk about fuel cells with end clients, a considerable part of the end clients want megawatt scale. They don't want a 10 kilowatt scale, etc. That doesn't mean that there isn't an actual market for the smaller scale. For 10 kilowatt fuel cells, for instance, for even up to 50 kilowatt electrolyzers, there is a market for them. But right now, the hydrogen market needs to be, there's the lifelong game of chicken and egg, where basically you need to actually have demand to be able to lower down costs, and to lower down costs, you need demand. It's just completely circular. And to be able to get that kind of demand, you shouldn't be producing in the kilowatts. We should be talking in the megawatt range. That's when we can actually reduce costs to make it go mainstream. And today we have clients which are demanding things in that range. And that's why I see the parallel in this.
So you would think it's the missing link to really start the hydrogen industry?
I would say it's at least one of the key links to it. I don't know if I would go as far as saying that this is it. If we have scale, then everything is going to be extremely easy afterwards. It's the freeways and what have you. But it is definitely one of the big keys to actually getting the hydrogen and fuel cell industries going.
Okay, so that's all sounds good. We want to go megawatt and beyond. However, if I look at the technology offered by Ceram Hyd, we're talking it's a fairly large electrolyzer, but we're talking 150K, so we're far from there.
Yeah.
What's Ceram Hyd approach on going from where you are at now, 150K, to megawatt scale?
Well, it's obviously like everybody else, there's a staged approach to it. Like our the first port of call is this 150 kilowatt that we are installing currently for a power to gas project with the RWE energy on it. The idea is to test that to see how it behaves in terms of cycling, in terms of like shutdown, turn off behavior on it. But then after that, we're jumping directly to the megawatt. It's basically a project of about possibly up to 2 megawatts that we'll be doing. And in that, there's a certain design features that we have introduced that make it possible. For us, there are I would say there would be two pillars for our technology. One, which is really the core of it, which is the membranes that we've developed. We've developed completely new membranes that are ceramic-based, but that contain polymers, so they are completely flexible. And they are made to actually replace and enhance the performance of standard types of membranes that exist in the market right now, like Nafion and or all perfluorosulfonated membranes. These membranes have the feature that, they can be produced in mass scale. Actually, not they can be. We are producing them essentially in mass scale. Not hundreds of thousands of square meters, but in the thousands of square meters. And they have an even higher performance and higher durability than Nafion. They're not sensible to water quality. Plenty of things that render them easy to scale up, and that's why we've been able to scale up from tiny membranes that are the size of the palm of my hands to bigger membranes to stacks of 150 kilowatt. And the second aspect that we're doing is actually inspired from the water industry, which I gave just now as an example. In the water industry, if you go, for instance, a reverse osmosis plant for desalination, you see there these big racks which have in them these big cylinders. These cylinders are spiral wound membranes that go as modules. You just simply plug them in. What that means is that essentially you can pack into a fairly small space an extremely high density for water treatment. And it becomes quite easy to actually maintain because you don't have downtime for the entire system. You take out a module, you plug in another. And we're doing virtually exactly the same. So now the electrolyzers that we're going to be building, the megawatt scale, where we should have the initial prototype ready in Q1 2014, would be essentially, imagine that you have a large bookshelf with many shelves in it, and on each shelf you're putting basically a stack into it, a hydrogen production stack, that gets simply plugged in. It's got all the outlets which are already there, coming on it, the water inlets, the gas outlets, etc. Everything is in there, all the electrical connectivity. You just simply plug the actual the stacks in there. When you want to increase size, you simply append more modules. You put more bookshelves there with more stacks on them. When you want to do maintenance, you take out one stack because you're not going to have 20 stacks that all fail at the same time. You're going to have one. Instead of making an interruption for the entire system, you take out one stack, you plug in another one straight directly in there, ensuring almost zero interruption for the end client. And you take the old stack, you fix it, you return it. So it ensures reliability, it ensures scale, and it ensures the ability to actually be quite modular. Increase the size as you need it, decrease it as you need it. It becomes fully modular.
So before I expand on that subject of the Lego approach, I'd like to call it. The Lego kit
approach, exactly.
Where you're building blocks. I just want to remember the public that this is a public forum, so you're welcome to ask any questions. Just raise your hand and I'll bring the microphone. But returning to this Lego approach, how is this novel? Without being too critical, we've seen a similar approach, I believe, in the telecom industry, in the fuel cell part more than the electrolyzer, but where, you know, they build on a drawer approach where, depending on the size you need, you add so many drawers of power. You know, you add 5K, 5K, 5K to build whatever you need to power those telecom stations. Mm-hmm. How is your approach different from that?
This is not straight out, it's not. This is cross-pollination, I call it. We are taking basically things that have worked elsewhere in the water industry, in the fuel cell industry, which have allowed people to go up in scale. We're applying it to electrolysis. Of course, there's IP behind the way that the entire system is conceived so that it is properly modular, that you have electricity delivered exactly as it should be, you have the fluids flowing as they should be. There is work which is involved in it, but it is essentially taking a concept that works elsewhere and applying it to scale up in the electrolysis business. So in that sense, it is using concepts that exist from elsewhere and using them here.
You're not creating something new, you're just using something that you know worked, and why not expand
when the wheel
on it?
exists, you don't reinvent it.
Makes sense, but I still believe though that your technology, the fact that you have a flexible polymer / ceramic membrane, gives you an advantage on following this concept.
The advantage is that essentially our modules, like so when you have this entire bookshelf Lego kit approach, each of the stacks is a 250 kilowatt stack. It can be made even bigger, but it's a 250 kilowatt stack, which means that essentially something that would be the width of this platform would be able to fit about 6 to 8 stacks. So we're talking about 1 to 2 megawatts. The width of this platform and a bit more than its depth. So it becomes, so you have the scale which is built into the stacks themselves. They're compact, they are capable of delivering a very high, they have a very high power density if you want, and are capable of delivering these, the actual hydrogen at high scale. And the fact that our membranes can be produced in scale, and this is something maybe our CTO will be touching upon. He's going to be making a presentation a bit later. He will be able to take you through the details on this. The membranes that we have, to give an example, like these membranes are rolled, the machines we use to actually roll the membranes, roll the dough that we make into an actual membrane, are the same machines that are used in the Danish pastry industry. No, there is no joke here, this is the reality. So they've been conceived to be things which are extremely simple to make. And that's why we've been able to scale up. You don't see that, for instance, with fluorosulfonated membranes like Nafion, etc., where it's an incredibly complex chemistry of fluorine and sulfonation, and then they have to actually do it at large scale. They have to be able to hold these membranes to be able to spray catalysts on them. There's a whole there's a whole number of things that intervene and that make the membrane easy to scale up. That's why we've been able to scale it up basically with very low budgets on it, and that make it very easy to put it into a stack, like to coat catalysts on it. It's completely dimensionally stable. You can actually make these stacks. So in other words, the innovation is that we have been able to make these Lego kit blocks. We can make the actual blocks that are of considerable size, and we know how to put them together into the bigger Lego house, if you want.
And I think it's important to mention with this whole Lego approach of building a kit, and you're really throwing some of the engineering work into engineering firms.
Absolutely.
Services.
That's again another thing that we have learned from other industries. Right now, if we look around essentially at most of the electrolyzer manufacturers or most of the people working on hydrogen production, everybody wants to do absolutely everything themselves, which doesn't work. You can't. There are things you can do, there are things you should be able to outsource. When we want to go for a company like ours, for instance, essentially a startup, a small startup which doesn't have huge resources, etc. If we get somebody who comes to us and he says, like, we want a 5 megawatt project, okay, we'll make the stacks, we'll make all the necessary designs and whatnot. We probably will even build the balance of plant. But then you actually need to take these things there. You need to install them. You need to make sure that they are that they satisfy all sorts of. I think I've lost my mic. No, it's back. You may have to make sure that they satisfy all sorts of certifications, that everything has been done to the standards required by the client. This is typically the work of engineering companies, big consultancies. That's how you see it normally. And big consultancies, they will not get involved if you're talking to them about a 100 kilowatt project. That doesn't make any sense for them in financial terms. And B, they need a certain scale at which you can actually deploy them. So this allows us to transfer these things to engineering companies and allows us to standardize also, which is an extremely important feature.
I think one of the other advantages to that, to kind of transfer the installation work and the turnkey project approach of a scalable electrolyzer installation to engineering firms, is that you're also taking away the high technology and understanding required of the stack itself, like of the electrolyzer. There's so much knowledge required to manufacture that portion. But if you give it to them in a contained block of a certain size and say, I've taken care of all how to put it together, you just make it as an overall integration system.
Absolutely, absolutely. The idea is like the engineering firm must not be in a position where they have to understand how the system is functioning to be able to install it, or even potentially to do low-level maintenance on it. It should be something where they don't really need to worry or understand, like, okay, this is how the electrolyte circulates inside the cells or what have you. It has to be extremely simple. They have to be in a situation where they don't need to acquire additional skills to be able to install and do at least low-level maintenance on it. Then it's easy for them to take it on. Then what they need to worry about are the things that we are not specifically qualified to look at. Permits, land, all sorts of like safety zoning and what have you that would be involved in it. That's where they come in. The idea is always you want to do what you are best at and let somebody else do the rest. And in this case, it would be the engineering companies.
And there should be a cost advantage to this approach as well, wouldn't there be?
Absolutely. There are huge cost advantages for it. When we have the cost advantages, you already see them when you're passing in terms of size. If you have a 100 kilowatt electrolyzer, I'm not going to give exact numbers, but just to kind of give an estimate on it. The cost per kilowatt today, I look at the bills I get from my suppliers, what it costs me, etc., etc. If the cost is, say, I don't know, 5,000 euros a kilowatt, when I go up to the megawatt scale, in terms of the actual economy of scale that I achieve on buying cheaper power supplies, cheaper tanks, etc., etc., I go down to basically 2 to 3 times less in cost per kilowatt. And it still continues all the way up to about 5 megawatts. You still get cost reductions on it. So effectively going up in scale diminishes your cost per kilowatt and eventually the cost per normal cubic meter of hydrogen, of course. It diminishes by 3 to a factor of potentially even up to 5. So there is a considerable actual economy of scale that's achieved.
So by going through this scalable system that can be built on building blocks like Lego, do you think it's existing industries such as the chemical industry, the food industry, that will adopt those systems first, or it's really going to be the first transition into the power to gas industry?
I think possibly the power to gas will be the first port of call for these large systems, because in the food industry, in the glass industry, in the metallurgy industry, we've had installations in the metallurgy industry, for instance, and there is some pressure there. So that's a bit of an exception. But for the remaining industrial uses of hydrogen, people are fairly more conservative. They need to actually see it tried out by somebody else. The power to gas requirements are considerably more stringent than the requirements of the other industries, such as food hydrogenation or even metallurgy, etc. So if it works there, that's more than sufficient proof for these industries to actually start adopting this larger size. So I think the power to gas is really the first port of call. And aside from that, that's where we see actual growth. That's the sector where we're not coming in to replace existing equipment. There is no existing equipment. We're coming in to put new equipment.
It's just starting slowly. We've heard a lot of projects of refueling station and taking over all the renewable energy concept from the wind towers. And
it's an approach that makes a lot of sense. There's in Europe overall, in Germany in particular, many of the Nordic countries, Denmark, etc., because there's a large amount of renewable energy, whether solar or wind, and that energy has to somehow basically, those installations that have been partly subsidized or considerably subsidized even, they need to actually pay for themselves. You need to increase the return on investment. To do that, you need to be able to use these installations all the time, not just when it happens to be there or when it doesn't happen to be there. We need to be able to use the wind energy at night. We need to be able to use solar at peak and at off-peak. So it needs to be stored. And today, the idea of being able to store it into the huge existing gas grid is a very good idea to improve return on investment. I think that's kind of one of the key things that is driving the growth there.
Well, unfortunately, we're actually running out of time, so I'll invite the public to join Dr. Nazar back at his booth, which is D61, and I'm sure he'll be more than happy to discuss further this subject with you. Thank you for your time, and please help me thank Dr. Nazar for his time as well.
Thank you very much. Thanks.
Thank you very much.
Thank you.